Good evening. This is our review for exam 3, which is on chapters 8 and 9. Sequences, series, and power series, focusing on Taylor polynomials. The goal of the first chapter, chapter 8, is to answer the question with converging or diverging. 50-50 chance, right? Except the alternating series, which converge in two different ways. Which ones? Conditional convergence or absolute convergence. The notion of absolute convergence is actually the convergence that you have for every single test. So when you talk about geometric series or telescoping series or integral test, all of those convergence means absolute convergence. That's what it is. So only alternating series have conditional convergence in addition to convergence and divergence. We have two sections on sequences. And sequence was the ordered list of numbers, which is ordered through the set n, set of natural counting numbers. And they have only one test to test for convergence or divergence, and that is the limit test. So you take the limit of an, and that is either a finite number, L, and we say sequence converges to that L, or it's positive or negative infinity, which gives us divergence. So sequences are very straightforward. Only one test for sequences. What you would need to know is how to combine, how to write an equation once you have the sequence given. Just like on your lab, you had those two problems where you converted the sequence, let's say 1, 1/2, 1/4, 1/8, and so on. You convert that into 1/2 to the n, starting at 0, right? So you will need that knowledge for sequences, and you will need also the knowledge of the only test that is there, which is the limit test right there. And then we are moving into series, and the series are the sum of the sequence, which means we have now summation of ak or an that can start at 0, at 1, at any value. And for this one, we actually have 10 different tests. Now, these 10 tests are listed in a textbook, the chart you have. And one of those tests is named the Divergence Test, or also end-term test, depending which textbook you're reading. And that's the one that should be tried first on every series you're trying to test. Because if the divergence test, yeah. So the order in which you try these is obviously if you're recognizing telescoping, geometric, or P series, you should do that, right? But as the rule of thumb, if the problem doesn't say use integral test or use ratio test, then you should try divergence first, because it literally takes 5 seconds for you to take the limit. And if the limit is not 0, it immediately, series would diverge immediately. So that's the first test you should try. Let's list all of the tests. So I'm going to list divergence test first. And then after that, we are going to take a look at geometric, telescoping, integral, P series. Then we have two comparison, direct comparison. And then we have the limit comparison, the one that is used most of the time. We have ratio root. And we have alternating. Remember, for alternating, you have to have -1 to the n or cosine n pi to make it alternating. And also alternating is the one that has a conditional convergence, absolute convergence, and divergence as the option, where all others have just absolute convergence, which is just shortly called convergence, and then divergence as choices. So 10 tests. Let me just make sure I have. We have 10 tests for series, and you should try the divergence test immediately for every single one, and then after that, whatever you find out. So I'll put some notes here. So try this first. For geometric series, the important note is make sure it starts at 0. If it doesn't start at 0, you have to do that shifting the parameter and all of that stuff. Telescoping, I'll just say partial fraction. So watch for that. So partial fraction decomposition. Integral test. Oof, if I could make this, so 3 conditions here. I can do it this way. 3 so proofs. P series. The note is way too easy. Nah, what the hell is it? Nah. No note. Direct comparison, the note says try limit first. And for the limit comparison, we'll say try this first. How about those notes, huh? Root and ratio have the same conclusions. Ratio tests, so factorials would go here. But you can also do geometric series with this, or and I'll say mixtures of functions. And then root test, if your AK is raised to some form of K, you will take the kth root of AK to the K, and they will cancel, and you will just have AK, and then you will do the test. So that's how you recognize. And now that I used all of the notes to be read, -1 to the n, or cosine n pi. So these are some kind of notes and pointers for you guys to easier get through the list. And for the last time, if you don't have the list of conclusions and conditions memorized, you are doomed. Exactly, that's the word. Because you cannot come up with this stuff, and hopefully so far you've seen that, you know, common sense sometimes leads you to the wrong conclusion. So try to retire the common sense. Gut feeling is okay. It's good to have the gut feeling of how the problem should go. But then, because you know the rules and memorize the conditions and conclusions of each test, you will be able to get there quickly. I've seen students who get very proficient with this, finish the exam extremely quickly, and then some obviously struggle for a very long time. So study that list, and then if you have a particular issue with memorizing, one or two or confusing them, well, make sure you read them right before the test, and as soon as you get the test, write those down, all right, on the back page, so that you have them available when the, stress kicks in, so you don't confuse things. You will always be able to single out very quickly geometric series because they have a specific form. You will always be able to single out p-series and alternating. Also root test because of the k's, right, exponent, and then ratio test for factorials. So those are the ones that you can immediately. The ones that are hard to spot are obviously both comparisons. Integral is by far the most annoying one to do because you have to do those 3 proofs, and that also gets to be either very short or very annoying depending on what kind of function you're dealing with, whether you know its graph or not, and then whether you have to do the calculus, right, to show decreasing and so on through the first derivative. So exam-wise, we should have at least 2 problems on sequences, at least 3 problems on power series in some form, and then the rest on series from chapter 8. About 10 problems, possible replacement question, again, depending on the level of the spice in the exam. And then some of the problems might say use root test, use direct comparison. But for the most part, the problems should just say, do the problem, right? In which case, you pick the test, you do the problem, and always remember that your answer is that sentence in the end, not the calculations and things you went with in between, because that's mainly algebra work. The answer is always what I used to box before. Since blah blah happened, your series converges or diverges by, and then you state the test you use. Obviously, if the problem says use the, root test, you don't have to say converges by root test because the problem is asking you to do the root test. So you don't have to, sure, write it. It's not a crime, but in that case, you don't have because problem was specific to ask for, let's say, root test. What else is there on the exam? We have power series, which introduce variable x within the series. And we've seen that one approximates the function. You've seen the first 2 terms of the Taylor polynomial in Calculus 1 under heading of linearization or the tangent line. But now we go to the infinity number of terms, and we know that we can take any function and turn it into a polynomial. And because there is a polynomial of infinite amount of terms, if we are calculating something, we are going to cut out vast majority of terms and maybe keep 3, 4, 5, depending on which precision you want. So then that's approximation in that case. So the last part of the exam would be on power series. And under that heading, so we are talking about the basic definition, so ck x to the k. You can start 0, go to infinity or anywhere else. And we are focusing on Taylor polynomials, so Taylor series, which is the summation 0 to infinity, the nth derivative computed at a divided by n factorial times x minus a to the n. That's the formula for it. And then we keep computing derivatives and plugging everything in. This one is centered at a. We can find the interval of interval and radius, sorry, interval and radius of convergence. Now, I told you always use ratio test. Technically, there are other tests that you could use. However, ratio test is guaranteed to work. In some cases, you might be able to use, I don't know, comparison or the root test, and they might be faster. But if you want, one size fits all kind of tool, it would be the multi-tool. It would be the ratio test there. And we need to know how to do calculus on Taylor series. Go. I spelled calculus with C's. See what you're doing? So calc with Taylor series. And that is obviously extremely easy because you will be taking the limit term-wise, taking derivative term-wise, taking the integral term-wise, and these guys are polynomials. So it should be literally no-brainer for you to solve calculus of these things. Where could you have issues with the power series? Well, if I am sufficiently bored to come up with 1/4 minus 3/8 plus, I give you something like that, and then you have to figure out what's going on.
Or you can read a really nice guy at the law. You do a little stuff.
Well, considering I got the cake.
What?
Considering that I got the cake.
You got a cake?
Yeah.
Someone gave you a cake?
Someone gave me a cake, a slice, yeah.
Okay. Oh, I think that's the worst for us to have. It's not so spicy.
Professor, what's your favorite cake?
Cake.
No, but like chocolate, just cake.
There is the category called cake. I hate coconut, but I'll eat the whole cake with the coconut.
Can this be the alternative for the 2.7 million?
I'm a foreigner. I did not get anything you said. You gotta speak slower.
Nothing. Nothing.
Did anyone hear what he said? Because now I don't know. See, I'm not alone. I think this covers the exam. As you can see, simple, right? 3 things. 11 tests and expansions. Take some derivatives around. Do you have any questions, any problems that are not on the lab yet we are to do? Let's see, like 7 hands went down. What's up?
For the integral test,
Yes.
would a graph of the function?
Remember that graphing calculators are not allowed. So if the function is 1 over ln x squared, good luck with the graph, right? How are you going to graph it?
1 over x squared.
I said 1 over ln x squared.
Well, then you wouldn't be giving us that because that would be impossible to do without a calculator, graphing calculator.
But you have the 3 proofs that you can do.
But we won't know if it's decreasing. And that's one of the
Yeah, you would. You find its derivative, and if the derivative is always negative, it's decreasing. What happened?
Yeah, there we
You
go
got
again.
that with the chain rule. Double chain rule. I know, calculus, well, see, you guys have no problems with Calc2. The problem is with algebra, and then Precalc1, and then Precalc2, and eventually Calc1. But no one has issue with Calc2, I know that. You're all good. Calc2.
If I can go back to my past self, I would just tell them to get everything else and just worry about algebra.
Exactly.
Who cares about everything? Algebra.
Algebra is the key, yes. So what is the derivative of 1 over ln x squared? Is going to be d dx, and then you rewrite this as ln x squared to the minus 1. So when you're taking the derivative of this, you first drop the exponent down, then you have the ln x squared to the negative 2 because you subtracted 1. Then the derivative of the inside is 2x over x squared because the argument, right? The argument goes as the function down, and then its derivative on top. One of the x's cancels, and we have negative 2 divided by x ln x squared. Very good. So this piece is always positive. I'm doing that analysis for integral test, right, for decreasing. So this one is always positive. This number is always negative. And this x is also always positive because you are dealing with values 1 and on, right? Your domain is 1 and on because ln x of 0 doesn't work. So the first value that you can use to compute the series which this function came from, well, sequence which this function came from, has to start at 1. So that's positive as well. You have a negative divided by a positive. This is always less than 0. And by the first derivative test in calculus 1, we know that if derivative is negative on the entire domain, you have a decreasing function. So you can find, if you are not sure how to draw the function, how to graph the function, you can actually take its derivative, and if derivative is always negative, then the function is decreasing across the board. If it switches, it's right. If it has critical points along the way and it looks like this, well then, right, it's not going to be always decreasing. So I don't know how 1 over ln x squared looks like, but I know it's always decreasing. So if I want to imagine that it will look like this, it will look like that, you know, but it's always decreasing. Does it have positive terms all the time? Well, it does because ln of x squared, where x is 1, right, will always give us 0 and more. So all terms are always positive. So positive decreasing, is it continuous? Sure, it is continuous because ln is a continuous function, x squared is a continuous function. Combination of continuous functions is continuous. You write it as a paragraph, right, 3 sentences. So those are the proofs for integral test if you don't know how graph looks like, and you can compute those. Please go back to the lecture on integral test, the video, and just look at, I believe I did 3 examples. 2 where I used the graph, and 1 where I did the full proof. And I just dictated the full proof for, I wrote 1 out of 3, but I told you how to do the other 2 verbally. So as you listen to this video again, and again, and again, and again, because the review videos have more hits than any other video, you will be having another example done. All right. Are there any? Yeah, I have one that has paragraphs written, right? Yes. Yeah. Are there any other questions regarding the exam? Yes.
When we look at the growth rates, those only apply to the sequences. You can't use those rules.
Well, the growth rates, you remember that the sequence is, right, when you have the function for generating the sequence is comparable to f of x. So the same growth rates affect taking limits of the functions. So yes, it's related to the sequence, so you can take the limit faster as n or k goes to infinity. That's what it is.
So then again with series, block that out. Unless you take
No, because you will be using them. You will be using a growth rate of functions to do limits. See, let me give you an example. I believe this was in a textbook. Understand? Okay. I was about to do something, and then the pen stopped working, so I had to reconnect. Oh, yes. So the question is k to the k divided by 10k factorial. All right. So something like this. This question is definitely screaming ratio test, ratio test, ratio test. But then you say, but my most amazing professor always said, check the divergence first, right? Which means limit k goes to infinity, k to the k divided by 10k factorial, well, is equal to infinity because this is the fastest growing function, and that's it. So now this is not 0, and because the limit is not 0, diverges by divergence test. So this problem you can solve in 17 seconds with writing by divergence test, or spend 5 minutes doing the ratio. You will get the same conclusion because the answer is divergent. But you could use the growth rate of functions, which is the question, right? Growth rate of functions to quickly solve this limit. Because you can't really do L'Hopital's rule here, right? Can't really do L'Hopital's rule. Yes, it is infinity over infinity, but good luck with, k factorial and stuff. So there's no derivative, it's not continuous, right? So growth rate of functions will get you to take this limit quickly. If it was flipped, then you are in ratio test, definitely. Because the limit would go to 0. K to the k is the fastest growing function. By growth rate of functions, we know that when you have the fastest one in denominator, it goes to 0. So the divergence test would be inconclusive, and you are stuck with ratio test. Then you must do a ratio test. If you get limit less than 1, it's convergent. Limit more than 1, it's divergent. Yes?
Is this something you were supposed to know the K to K and take back for?
Yes, because of the growth rate of functions. That was the question. I believe we did that one in P series. No.
It was before the second exam. So I have it wherever you can read it.
Oh, yeah, I remember it. In 8.2.
Yes. There it is. Growth rates of sequences in 8.2. So k to the k is faster than k factorial. Are we agreeing on this? Great. Joe.
Are we gonna have any like composite power series or the power series? Remember we talked about like here's an example like e to the x squared.
Quite possible, yeah. Because you expand the power series and you just replace x with whatever. It's like U substitution, technically. That's what it is. It's like U sub. You take out the exponent, let's say, you don't like, or the argument of ln you don't like, or whatever it is. You can call that U. You can expand, having instead of xu as a variable, and then replace whatever was 2x or x squared for each one of the u's. If that's going to make it better, sure. So it's possible to have the composite power series and then take the derivative or integral. It's possible to have shifting the counter for geometric. It's possible to condense those strings of, you have the 1 and then 1/2, 1/4, right? To put it back in the formula. All of that stuff is there. That's the part of the chapter.
How about anything with remainder?
I might ask, yeah, see, that's one thing I didn't write. Remainder, that's the next term, right? So if I ask what is the remainder for the, I don't know, third term or the fourth term, you calculate that term, plug the value in, and you see what the number is. Yes?
Are you going to ask possibly about the sums for geometric series? So I know we have.
Oh, I didn't write that.
One over A
The answer for that is hell yes. Here in blue. And A over 1 minus R. Right?
Yeah.
For the sum. So make sure it starts, well, it kind of implied because it starts at 0. The only reason why you have to actually suffer with shifting the counter is to actually have a correct A so that you can apply this formula. If the question for geometric series says test for convergence or divergence, no one asked you for sum, so it doesn't matter at which number it starts. You don't have to shift, you just say convergent or divergent because that's what the question asked for. But the question can also be test for convergence or divergence, and if it converges, find the sum. In that case, if your geometric series is not starting at 0, you have to shift the counter because that will change the value of A from the original one you had to the new one that you actually need for the formula. So shifting the counter happens only if if the counter doesn't start at 0, but you don't have to worry about it unless it's asked for the sum. Make sense? Great. Anything else?
Calculus makes me depressed.
I can put that on the test.
How much money do you need? Yeah, like I think it's like what, 3.7?
3.7 million this year, yeah.
American or
He goes
pesos?
Sorry?
American or pesos?
American.
Oh,
I see investments. I mean, it's driven by the market. Nothing I can do.
well, you like, if I give you $2 million in gold, and you eventually get
It's heavy. I don't like to exercise and drag things around.
What if I gave you my Steam guaranteed stock with over $300 worth of games in it?
And then you have to multiply that by 10 to the fourth somehow.
Probably already has Probably. I was very lucky.
Any other questions that are related to the exam, which is coming up on Monday? You have the SI session before the class, which is good. And I hope you guys show up for that. Anything else? 10.1. You opted for it tonight, right? So after the exam, exam will be for hour and 20. That's the standard time. Hour 20 to hour 25. I extend it usually 5 minutes. And then after that, we'll do 10.1, which is parametric equations. And then the next class we'll do the last two, and then the following class we'll have for the review. And then if you need one more review, we can do that as well. So we have time. Anything else for the exam? It will be printed on paper. Bring your pens and pencils. No graphing calculators. And is there anything else? Memorize the sheet. Make sure you know all of them. You guys have 10 tests for series and 1 for sequence, which is the limit test. Which one do you start with? divergence. You check every single problem with divergence. Now, if the problem says use the integral test to solve the problem, well, you can still use divergence just to kind of have a sneak peek, right? Because if it diverges, you know which answer you're hunting for with your integral test. That should be, right? Should be common sense. Hopefully. I don't know. So you can run that divergence test against every single series problem from chapter 8, and then go back and make sure that you did the ratio test if the problem says use the ratio test and so on. Alternating series, obviously you have those two conditions to get you on the convergence track, and then you have to test for conditional or, right? So I hope you remember the tree and how it branches, which path to take. Anything else? Me neither.
I might cry before the exam, Professor.
I usually cry after the exam because I gotta look at those. So we all cry together at different times. All right, so that's the end of the review. Back to the lab. Bye, stream.